Hello. In this video, we are going to analyze an air standard diesel cycle. I have already drawn the TS diagram for the cycle. Just to remind you, 1 to 2 is our isentropic compression stroke. 2 to 3 is constant pressure heat addition process because fuel is getting injected, pressure remains constant, and 3 to 4 is isentropic power stroke. In other words, power is delivered both by 2 to 3 and 3 to 4, both these processes. And 4 to 1 is constant volume heat rejection process. Well, I'm assuming you're familiar with the Otto and diesel cycle. They're covered in chapter 7 of your textbook. In this particular problem, plenty of information supplied. State 1 is given to us except for the mass in this problem. So we'll just assume 1 kg of mass trapped in the cylinder. We'll base the problem on 1 kg because none of the answer really depends on the mass of the cylinder, mass of the gas inside the cylinder. The maximum temperature is supplied. That will help us find state 3. And so basically we can now proceed. It is assumed that I've already logged in that you're familiar with obviously the app to solve this problem is we follow the specific IC engines and reciprocating cycle branch and click PG model to launch our gas model. In this particular problem, we are asked to use the cold air standard cycle, which means CP and CV remain constant, that is PG model. Well, it is assumed that you have gone through the example of Otto cycle because this solution almost mimics what we have done in the Otto cycle example. Okay, so we launch. This is the same app for both Otto cycle or diesel cycle, for any reciprocating cycle for that matter. Air is the default fluid, so let's begin. We'll assume a mass of 1 kg, which is no bearing on the solution. 95 kPa is our initial pressure, and 20 degrees Celsius is our initial temperature. State 1 is found. And because we need the compression ratio and maximum temperature as a parameter, so let's introduce R equals 20. This is our compression ratio, volumetric compression ratio, and T max. Maximum temperature is given 2000 degrees Celsius, but we better convert that to Kelvin. The SI units in test is always used in the IO panel. Okay, so if you click a calculate, it registers these values. So now we can go back and calculate state 2, knowing that mass, of course, remains constant, M2 equals M1, and volume will become. To save time, I have already calculated the other states in a separate panel. I'll just lead you there. So state 2 and state 1 we have just finished. So state 3, let me just walk us over what I have done. So state 3, pressure is of course is isobaric process at constant pressure heat addition. That's our fuel injection, and maximum temperature has been supplied. So these are my input along with mass. That completes the state 3. State 4 is isentropic to state 2. Therefore, we should have S4 equals S3. Isentropic to state 3 is isentropic expansion, and the final volume must be equal to initial volume to complete the cycle. So we are back to state 1 as far as volume at the bottom dead center at that time. So now that we know all the states, it's good to always check on the graphics panel to make sure that what we expect, 1, 2, 3, 4, the TS diagram, the cycle looks reasonable. We go to the process panel, and for process 1, which I have already done, you can see that I've loaded state 1 as the begin state, state 2 as the finish state, beginning state and finish state. Of course, by default, there is no other type of work. And isentropic means, of course, adiabatics, Q equals 0. Therefore, external work, is all of which is boundary work, is calculated from solving the energy equation. We go to the process 2, which is constant pressure heat addition. You can see that again state 2 and 3 are the beginning and finish state, final state, and this is always 0 in every process. There is no shaft or electrical work anywhere. It's all boundary work. Of course, the SGN is negative because the boundary temperature is ridiculously low. We are heating the fuel to 2000 degrees Celsius. So obviously, the boundary temperature should be hotter than 2000 degrees Celsius. That explains why this is negative. It has no bearing to the solution, of course. It just points that something is wrong in this panel. So if somebody says find the entropy generation, that will be totally wrong because it cannot be negative because the boundary temperature chosen is pretty bad in this problem. But you can just switch it to say 2000 Kelvin or 2000 Celsius or more, you'll find this will turn positive. Okay. For process 3, which is from 3 to 4, that is your isentropic expansion, and therefore isentropic expansion means SGN must be 0. The boundary work delivered by the power stroke, the isentropic expansion stroke, is shown here. So notice power is delivered in process 3 as well as process 2 in a diesel cycle, as opposed to Otto cycle. Process 2, there is no power delivered because it is constant volume heat addition in Otto cycle and is constant pressure heat addition in diesel cycle. That's the primary difference between the two. And of course, process 4 is blowdown. What happened there is that heat is rejected at constant volume, 4 to 1, and you can see heat transfer is negative because heat is rejected. When all these 4 processes have been calculated, cycle panel automatically compiles everything. So you can find, for instance, what's your thermal efficiency? Very high, 63.27. Diesel cycle typically have higher thermal efficiency than Otto cycle because of higher compression ratio used. And all the other parameters such as MEP, etc. have been found. To find the cutoff ratio, we can go to the IO panel and declare a variable, say, our cutoff, our our cutoff must be volume at 3 divided by volume at 2. That's by definition is the cutoff ratio. That is, what is the volume at the end of fuel spray heat addition versus the volume at the top dead center. So the cutoff ratio is found to be 2.33, and everything else we want to know about the cycle is found. So suppose, the question is what will happen if the compression ratio is not 20. Suppose we reduce it to 15. Well, it's so simple. We can just say, calculate to register the change, make sure we didn't make any mistake, and let's make sure we remember, write down what is the efficiency right now. It's 63.27%. So if I do a super calculate, you will see efficiency will surely go down. It became 57%. So you can see how sensitive efficiency is to the compression ratio of a reciprocating cycle. Now you can perform any number of parametric study in this manner.